Today we're looking at the topic of similar triangles. I'd like to start by demonstrating what is meant by similarity. In English, we say that two things are similar when they are a little bit alike. They sort of share some sort of characteristic. In maths, similar actually has a really specific definition. I'm not going to worry too much about it today, but basically the way we use the word similar in maths is slightly different to how we use it in English. So shapes are similar if they are effectively exactly the same shape, like all the same angles and stuff, but one's an enlargement of the other. One is bigger than the other. So you achieve this in... I've got Microsoft Word open here. I can make the shape bigger if I do this kind of thing, but notice how I've just stretched it, and that's not an enlargement, and so the original image and the one that I've got on the screen now, they're not similar. Okay, we wouldn't say that they are mathematically similar. Similarly, if I stretched it in the other direction, okay, if I stretched it this way, that's I've made it bigger, but that's not an enlargement. They're not similar. It's a bit like you get the corner of it. Okay, and when I get the corner of the shape and make it larger, it doesn't pull it out of proportion at all. Everything sort of snaps into the same ratio still. So if I just undo that and have two copies of the same thing here, these are identical copies. And then if I make one bigger using the corner, this one on the right here is an enlargement of the one on the left, and we say that these two shapes are similar, these two photographs in this case are similar because one's an exact enlargement of the other. A couple of extra things to notice about it. If I just undo that enlargement, and instead I grab this corner and I make it so I can make it smaller, that's fine. That's because now the one on the left is bigger than the one on the right. So we've still got similar shapes here if I make it smaller. But look what happens if I sort of go past this point here. The computer sort of flips it over, or if I do it like that. I don't know how clearly you can see on my image here, but the one on the right, it's an enlargement, but it's also reflected. It's also reflected. And when it was up here, if I undo that again, when it was sort of up here, it's an enlargement. If I bring it back down, but it's also rotated. Okay, so the one on the right is larger than the one on the left, but it's also rotated. So my analogy continues correctly that if you drag it from the corner to make it bigger, it doesn't matter if it reflects, and it doesn't matter if it rotates. All the time you've got one being an exact enlargement of the other, without sort of stretching it out of proportion, we have similar shapes. I could even rotate it using this tool here. Okay, and they're still similar shapes. They're still similar shapes. Right, now, so here's an example, perhaps more typical of the sort of questions you'll deal with, where I've got two triangles, and I'll tell you that the one on the right is an exact enlargement of the one on the left. So suppose I'd photocopied this, and on the photocopier I'd enlarged it, and that was the result. So it's an exact enlargement, or you can imagine that I put it in Microsoft Word, I dragged it from the corner, and I achieved this shape over here. So one's an exact enlargement of the other. The first thing to do is to figure out, well, how many times bigger has the shape got? How many times bigger all the lengths are is called the length scale factor. I'll put that over here, length scale factor. And that simply is how many times larger. So what do you multiply the lengths by? How many times larger are all the lengths on the right triangle than on the left triangle? Now you're supposed to realise that they kind of match up. We call these corresponding sides. So the 1.8, when you enlarge it, becomes 3.6. So the 1.8 and the 3.6 are what we call corresponding sides. That's a special word, I'll put that there as well. Corresponding sides. The 2.7 will match up to this one that's currently called x, and the y will match up to the 3.2. If it's not completely clear, you'll sometimes be given markings like this. They might say that these two angles are the same. We don't know what they are. Maybe they're 30 degrees, maybe they're 24 degrees. Don't know what the angle is, but we're just being told that they are the same size, whatever they may be. And I might be told that these two are the same as well. So the markings are like little arcs or double arcs, that kind of. I could even put triple arcs in, I won't bother. But you can see then how they match up. So the y is the same. So the y corresponds to the 3.2. So the 2.7 corresponds to the x, and the 1.8 corresponds to the 3.6. Right, so I claim that for this particular one, it should be fairly simple to see that the scale factor is 2. As if you double 1.8, you get 3.6. But if you can't see it, then step 1 is always divide the big side by the small side. So length scale factor, I'm going to abbreviate that to LSF. Just do the big side divided by the small side. And I don't mean do any old big side divided by, I mean corresponding sides. So I'm going to pick the 3.6 and divide it by 1.8. And your calculator will tell you that that is 2. So that means if I want to go from a length I know on the small triangle to a mystery length on the big triangle, I need to multiply by 2, because these are all double the size over here. And similarly, if I wanted to work out a mystery length on the little triangle, I'd divide by 2, anything from the big triangle. So I hope it's fairly clear then that you get x by doing 2.7 multiplied by 2, 5.4 units centimetres. And for the y, I'm going to halve 3.2, which is 1.6. Okay, so to get something on the big triangle, you multiply by the scale factor, and to get something on the little triangle, you divide by the scale factor. I'd like to take you through a few more examples, because there's like little fiddly bits that will happen as we go along. Brilliant, so here's another pair of triangles, and the question is the same as before, just find any missing lengths that are labelled. Here I'm only interested in finding x, not interested in anything else. You'll notice that this is a situation where one triangle is bigger than the other, so we've got this similar thing going on, but it's also reflected as well, and that's okay. It doesn't matter if it's reflected or rotated, you still have similarity going on here. So the first thing really is to figure out, well, how many times bigger are all the lengths on this triangle than on this triangle? So I need to divide a big length by a small length, but I need to figure out, well, what does this one even match to? Okay, this length of 6, should I divide it by 4? Should I divide it by 3? Should I divide it by 5? So the first thing is you've got to figure out, well, what does this even correspond to? That's where these markings help us. So the 6 that we know on the big triangle, that's the length that goes between the angle that's marked with a double arc to the angle that's marked with the right angle symbol. The one that does that on the other triangle is this one up here. So it's the 4 that connects the angle marked with double arc to the angle marked with the right angle symbol. So the 6 and the 4 are corresponding sides, and it turns out that actually this was a reflection and not a rotation. Great, so length scale factor is the first thing I'll do. So it's 6 divided by 4, big side divided by small side. That comes out as 1.5. So all the lengths over here are 1.5 times bigger than all the lengths over here. I don't know if it's now obvious, but the x connects the single arced angle to the right angle. So that's this one over here. The x corresponds to the 3. Those two there are corresponding. So to figure out what x is, I'm going to do 3 times 1.5. Multiply by the scale factor because it's on the bigger triangle. And it comes out as 4.5. This time the units are meters, so be careful with your units. So x is 4.5 meters. Right, third example then, same idea again. I'd like to find x and y. So I don't know this length, I'd like to figure out what it is. Don't know that one, I'd like to figure out what it is. This time I'm not going to tell you that the triangles are similar, but we know that they are similar because this line is parallel to this line. That's what the little arrows mean, remember? And so some of the other maths that you learnt, in fact probably quite a while ago back in year 7, if you've got parallel lines, then we know that this angle is the same as this angle. That was a rule called alternate angles. We know that this one is the same size as this one by alternate angles. You might have called them Z angles, Sometimes alternate angles are known as Z angles. And actually these two are opposite angles as well, so they're the same size. Well, because all the angles are the same, it must be the same shape. Clearly this one's bigger than this one, so it's not exactly the same shape, but it is the same shape as far as we're concerned. One's enlarged, this is similar. Okay, we've got the similar triangles situation. So step one, same as before, let's work out how many times bigger the big triangle is than the little triangle. So the matching pair is this sort of base here. So I've got this, the 9 and the 5 that correspond. If you can't clearly see it's the 9 and the 5 that correspond, then check that the 9 connects angle that's marked double arc to angle that's marked single arc. Well, so does the 5. It connects angle that's marked double arc to angle that's marked single arc. So the 9 and the 5 definitely correspond. 9 divided by 5, I think, is 1.8. Okay, so all the lengths on the top triangle are 1.8 times bigger than all the lengths on the little triangle. So the little triangle has been enlarged, scale factor 1.8. It's also been rotated, can you see that? Because the one that was bottom left has ended up being top right, so it's been twisted around as well. X is on the little triangle, so to get X I need to do a division. Be careful, X links to this one here. It's the 10.8 that links to the X, because can you see it's single arc to dot, single arc to dot. So I've got to do 10.8 divided by the scale factor. I might do a calculator for this one. So 10.8 divided by 1.8, 6, exactly 6. So I know that X is 6 feet in this question, slightly different units. And for Y, well, Y is on the big triangle, so I need to multiply here, and the Y corresponds to the 4.7, so it's 4.7 times 1.8, because I'm on the big triangle. 4.7 times by 1.8, 8.46 feet. Okay, one last example then that's got some other features. So in this question there are two similar triangles, but they've been put inside each other. The small triangle has been slid inside the big triangle. So that'd be like when I was showing you at the beginning with the photo of my classroom and I enlarged it, it would be like putting the answer back on top of the other one, putting the small one back on top of the big one once you've enlarged it. But no sweat. So once again, I've got parallel lines going on. It turns out that that angle is the same as that angle by corresponding angles this time. This angle is the same as this angle. And the one at the top is shared between both of them, so it clearly fits exactly inside. This time I'm told that the length on the little triangle is 5.7, and I don't know the length on the whole length of the long side, so it's a little bit more complicated, this one. Sometimes it's a good idea, if you can see it anyway you don't have to, but sometimes it's a good idea to actually draw the two triangles out separately and in the same orientation, so that if one's been reflected or rotated, you could rotate it back again. So I'm only doing this as a sketch. I've got this little triangle here that's base of 6 and a 5.7 over there. Don't know how long that one is, and I could do that better, couldn't I? Okay, so that's the little triangle, and the bigger triangle, base of 10, and I actually don't know anything else, do I? That's all I know for the big triangle. I know the big triangle has a length of 10, and then no idea. Right, so what can we work out? Well, we can work out the length scale factor. I can still do that, because I've got corresponding sides. The 10 and the 6 are corresponding sides. So 10 divided by 6. Now this time something interesting happens. If you do 10 divided by 6 on your calculator, it comes up with 5/3. If you want that as a decimal, it's a recurring decimal. So my advice to you would be to just not use the decimal at all, just keep the 5/3. If you're going to use a calculator anyway, the calculator doesn't mind using a fraction. So let's use 5/3. That means all the lengths over here are 5/3, or 1 2/3 times bigger than all the lengths on the little triangle. You'll notice then that X is how much it's sort of how much longer this long side is than this short side. So I'm going to work this out first. Let's work out how long this whole length here is. I shouldn't call it x, should I? I'm already using it. Let's call it y. Let's figure out how long this whole length here is. I'm calling this whole length here y, and that's what I'm working out right now. Okay, well, to get y then, that's on the big triangle, so I need to do 5.7 multiplied by 5/3. So I've still got the 5/3 on the screen, so I'll multiply that by 5.7. It comes out as 9.5. So I get 9.5 as the whole length. Well, x is just this little bit. So if I know the entire red length here is 9.5, I just take off 5.7 to leave me with the x. 9.5, take away 5.7. And I'm left with 3.8. This time the units are millimetres. All right, so there's a few things to be getting on with there then. I'll just briefly summarise. This was example 1, and these are two similar triangles in the same orientation. Nothing more complicated than we've enlarged that and then dumped the answer there. We haven't reflected it or rotated it. We've simply enlarged it, and these are drawn the same way round. It was important to work out how many times bigger all the lengths were on the big triangle than on the little triangle. That's called the length scale factor, how many times bigger. And furthermore, it's important to know which sides match to which other sides. That's the notion of correspondence. So that length there matches to that one there. We say the 1.8 corresponds to the 3.6. If you want to work out the length scale factor, sometimes it's just obvious. I hope you can just kind of see that that's doubled. I really hope you can see that that's doubled. But just in case you can't, do big side divided by small side. It's sometimes less obvious, like it was in the next example. So in this one here, less obvious because, well, two reasons really. First of all, it wasn't clear which ones matched up. But even then, you might not instantly know what you multiply 4 by to get 6. It turns out that you multiply 4 by 1.5. to get 6. Notice how not only was this one bigger, it's an enlargement, but also it had been reflected. And in this example, this one at the top is bigger than the one at the bottom, but then the answer was rotated, and they sort of stuck together at a point in such a way as the bases ended up being parallel. And finally, in this situation, when they're sort of stuck together, when the answer to the enlargement is sort of inside the other one, it can be a good idea just to split them out, just draw them both out. Notice how I didn't bother grabbing my ruler or anything. This is just to help me work it out. So this is just a sketch that helped me do it. The final thing to note is sometimes your scale factor comes out as a fraction, and that fraction might be easier as a top-heavy fraction rather than a recurring decimal. If you want to use the recurring decimal button on your calculator, go ahead. I don't even have one on this calculator. Okay, on this version of the Casio, there isn't a recurring decimal button, so I have no real choice but to use the fraction instead. Right, best of luck. Apologies for the long video, but I wanted to get it all in, so very best of luck.